In previous videos, we have talked about amplitude modulation, which is basically a linear modulation scheme. Amplitude modulation had a lot of different variations. We talked about the one in which we suppress the carrier and then transmit for example, ad hoc communication systems. Also, we have AM broadcast in which we send the carrier, that is AM with large carrier. Yet another application is a TV video signal that is in terms of the vestigial sideband. Now assuming this is our message signal and this is the carrier. For simplicity we have considered both to be single tone. Carrier is definitely at a higher frequency as compared to the message signal. So in amplitude modulation, based on the amplitude of the message signal, an envelope is established linearly. Presently, we are going to talk about some non-linear analog modulation schemes, specifically angle or exponential modulation. Angle modulation has basically two different types. The first one is frequency modulation, FM, and the second one is phase modulation, PM. FM has a number of applications, including the one that you have with you in your vehicles or handheld radio devices, that is the FM radio, which operates at around 88 to 108 megahertz, and also we use it in TV signals. Specifically, audio signals of TV are based on the FM, owing to a good noise tolerance of FM as compared to AM. Now regarding phase modulation, it is primarily used in digital communication, including digital video broadcasting terrestrial. Note that FM and PM, that is both of them, are dependent on the message signal. If the signal has a higher amplitude at a particular instant, the instantaneous frequency will be high, and when the magnitude of the message signal is low, then the frequency would be low. So the maximum and the minimum frequency is basically governed by the positive peak and negative peak of the message signal in the frequency modulation. In fact, frequency modulation and phase modulation are basically linked together by means of calculus. So it is often difficult to observe and classify the modulated signal as being modulated with FM or PM unless you know the scheme in which it was transmitted. So we will elaborate on both of these schemes in this video. So in modulation we have amplitude modulation and angle modulation. So in amplitude modulation, if we send a signal S of t, the amplitude is varied with respect to the message signal. However, in angle modulation, the amplitude is kept constant while the angle is varied with respect to the message signal. This is the major difference. So what are the benefits of moving from AM to FM and what are the drawbacks? There is a common misconception which states that the bandwidth of angle modulation might be less than AM, but this is not the case. At best, it is equivalent to AM, and usually it is greater than AM. So, angle modulated wave or signal is occupying more bandwidth as compared to AM. Now, if we are going to lose on the spectrum by utilizing more bandwidth, what are the benefits? The answer to that is robustness, or what we call the resilience of FM modulation scheme in terms of noise. If we are sending a signal over the air, because of the channel conditions and ambient noise of transmitter and receiver, the amplitude which governs the envelope, specifically for AM, that may get attenuated or degraded. So we will lose the information. But in angle modulation, the amplitude is not conveying any information. In fact, it's the phase which is conveying information. So small changes in the amplitude of modulated signal would not have any influence on the received signal, and hence it will be more resilient. Therefore, we will lose on the bandwidth in FM, yet we gain on high-end quality reception and reliable data communication. So why do we call it angle or exponential modulation? As mentioned, the message is basically conveyed in angle rather than the amplitude. Note that angle modulation can also be written in terms of real part of exponential j theta of t, right? So if you open this, it will become cos theta plus j sin theta, but the real part of it would be simply this one. So therefore it is called exponential modulation. One of the most significant aspects of angle modulation is to understand the concept of instantaneous frequency. As mentioned, the message signal is basically embedded inside the general angle. So if we plot the angle with respect to time, so it would show some kind of a non-linear behavior. So this is theta of t with respect to t. Now assuming we pick this point, so we extend a line crossing through it like that. This line will be intersecting the y-axis at theta naught, right? So we may call this as omega ct plus theta naught. So this is something which is showing in a linear behavior, and since it's showing a linear behavior, we have observed this in AM. If we take the derivative of this one, so with respect to time, to d by dt of this one, so we would simply have a constant which is omega c, right? But over here the angle is the generic angle which is constantly changing. So if we start at this point and we take another increment after delta t, so we say that we are trying to find the rate of change of this angle. That is theta of t being subtracted from theta of t plus delta t with respect to delta t. So this is something which we call as rate of change. Since it is in f, we can just multiply 2 pi in the denominator. If we let delta of t approaching 0, so that would mean that if we limit and say delta t tends to 0, f delta of t. So this is something which is a very small step, and this is something which we call as instantaneous frequency, or Wi of t in radians per second. So we are interested in this instantaneous frequency when we are talking about frequency modulation. So the instantaneous frequency omega I of t or Fi of t is basically equivalent to the general angle over this interval. From this we get an explicit expression of instantaneous frequency with respect to the generic angle. So that is omega I of t is nothing but d by dt theta of t, or also this theta of t is an integral minus infinity omega I of lambda d lambda. For simplicity of analysis, in the forthcoming discussion, we will set this theta naught, the intercept, equal to 0. Right. So now this brings us to the two types of angle modulation, namely the frequency modulation and the phase modulation. So in frequency modulation, the instantaneous frequency is directly varied with the message signal m of t. That is, the instantaneous frequency Wi of t is Wc plus kf m of t. So this is the message signal. This is the argument which was left after taking the derivative, as we have mentioned over here. So if you take the derivative over this point, this line would be exactly similar on this interval as the generic theta of t, right? So over here what we are mentioning is that if you take the derivative, you would simply have omega c, the instantaneous frequency, right? So this omega c is coming from the instantaneous frequency, and then you add message signal and then you scale it with a sensitivity constant which is kf. So the question is, why do we need the sensitivity constant? The answer to that question is that with the message signal, how much you want to increase the frequency or decrease it. For example, in this particular scenario, so if the message signal goes up, by what degree the oscillation should increase? If we reach a peak, so how much increase in frequency should be there? And if it reaches a negative peak, so how much decrease in the frequency should be there? So this is basically governed by the constant kf, right? So this is our angular frequency. Remember, we're going to send a signal s of t through the antenna, which is having a constant amplitude but theta of t. So this theta of t is being varied with respect to the message signal. So the relationship over here is, if you take the integral of it, so you will get theta of t, this would become omega ct, and we would have the constant coming out of the integral minus infinity to t m of, say, lambda d lambda. So that would be the angle. And so if we are sending the message signal, say s frequency modulated signal, so we would have a cos omega ct plus kf m of lambda d lambda, right? So this is basically our fm. Similarly, when we're talking about the phase modulation, in phase modulation, the angle is directly varied with message signal m of t. By that, what we mean is that this theta of t is simply omega ct plus, originally we had theta naught, but I have mentioned that we are making it 0. We are considering the intercept at 0. So this is just generic. You can keep it, you can remove it, it's up to you. But what we're doing is we are directly changing the phase. We are adding something over here. So this is something which relates to the change in phase, and then we are multiplying it with a constant kp. So the message signal, it directly changes the phase of the modulated signal. So in short, when we're going to send PM modulated signal, so we would have a constant amplitude multiplied by cos omega ct plus kp m of t, right? So this is basic difference between the two. So you may say they are almost the same. One is, they are related by calculus. So one is the derivative of the other one, or other one is simply the integral of the first one, right? So since we got this one, so we also can achieve the instantaneous frequency wi of t, which is the derivative of this one. So that would simply give us wc plus kp, which is constant, so it will come out of the derivative, but now we have m dot of t. So this is something that we will get. So we have now all the relationships. We have the instantaneous frequency, the phase, and the transmitted signal. And similarly for PM, we have the angle, the instantaneous frequency, and the transmitted signal. Right. So as a summary, we have this table that summarizes the discussion so far, that is between phase modulation and frequency modulation FM. The parameters of interest are angle and the instantaneous frequency. So if angle is basically directly proportional to the message signal, then you would have phase modulation. When the instantaneous frequency is directly proportional to the message signal, then you would have frequency modulation. But you would see that there is a very direct relationship between the two. They are linked by means of differentiation and integration. Next, we will talk about the system block diagrams of both phase modulation and the frequency modulation. Specifically, when we are mentioning phase modulation, let us start with the message signal m of t. So you can observe that the message signal is being multiplied with a constant which we call as Kp. This is a sensitivity constant. So if we are plotting a block diagram, we have a message signal that is multiplied with a constant Kp. Next, this constant, this whole thing is then summed up with the carrier omega c. This omega c is coming from an oscillator. So over here we have omega ct and we have that summation block over here. So once we add them up, then we get this angle theta I of t. Remember, when we send a signal through an antenna, we are sending a cos theta I of t. So that means that we are again multiplying with a gain of a, and then we have a modulated signal, that is phase modulated signal. Similarly, when we are sending an FM signal, frequency modulated signal, so we start with the message signal m of t and then pass it through an integral. So once it is passed through an integral block, we multiply with a sensitivity constant kf. So the message signal is passed through a linear integral, and then after that it is multiplied with the sensitivity constant kf, which is then added with the carrier frequency omega ct multiplied by gain, and eventually you get a modulated FM signal. Both frequency modulation and phase modulation are inseparable. So you could use a phase modulator to transmit a frequency modulated signal. I would repeat, you can use a phase modulator together with an integral block to eventually generate a frequency modulated signal. Otherwise, you could use a frequency modulator cascaded with a differentiator to eventually send a phase modulated signal. So you could use one to generate the other one, right? So why is it so? So it is quite evident from this block itself. So let's talk about the first case, using a phase modulator to generate a message signal. So starting with the message signal m of t. So if we are going to start with message signal m of t, you pass it through an integrator, and then you get a new waveform. Let's call it m tilde of t. So once you got this, now this becomes your new signal. Now you can put this signal over here and use the phase modulator to eventually generate a frequency modulated signal. So what I'm trying to say is that you could start with the message signal m of t, pass it through an integrator, you will get a new signal. Put that new signal in a phase modulator, right? But since the original signal has passed through an integrator, we would eventually get a frequency modulation. On the other side, if we start with the message signal m of t and pass it through a differentiator d by dt, so we'll get m dot of t. So once you got m dot of t, this is now your new signal. Now if you pass it through a frequency modulator, so you have a differential and then you have an integral over here. So both of them would cancel out. So once they are cancelled out, you will be getting a phase modulated output signal. So it is quite interesting. If you have either of the modulators, you could eventually get both phase modulation and or frequency modulation, but you would need either an integrator or a differentiator. So they are in a way inseparable. I have also previously mentioned that just by looking at a waveform, let's go back to some original slides in the beginning. So what I'm trying to say is once you receive a signal on the antenna, you receive a signal. So if you receive a signal just by looking at these two, we cannot judge whether the original transmitted signal was phase modulated one or frequency modulated one, right? So we need to know which modulator was used in the first place to in order to detect. Now let us look into a Simulink environment for FM modulator. So GFM of t is equal to A cos of omega ct, the carrier frequency, plus Kf, the sensitivity parameter, and integration of m of alpha, which is basically in our case this signal m of t. So it's integrating from minus infinity to t, and then our argument of the cos function is closing. So this whole expression is basically implemented over here in the Simulink. Starting with the message signal, so I have considered a simple sinusoid. This is a sine function. I have set the amplitude equal to 1. This is simply 2 radians per second, and I have set sampling time equal to 0.001. Note that these blocks can be obtained from library browser, right? So this is our message signal, and then we have Kf, that is the sensitivity parameter. So this is represented in terms of a gain block, and I have set the value of that equal to 10. Okay, so note that this is not Kf, this is Kf by 2 pi. So Kf by 2 pi is equal to 10. Next, what we have is we have a carrier frequency. So what I express over here is in terms of hertz, that is fc rather than omega c. I set it to 20. So message signal was at low frequency at 2 radians per second, while the carrier frequency is at a higher frequency, that is at 20 hertz or 40 pi radians per second, right? So then we have a summation block here. So that summation block is expressed over here. So all of these three blocks then multiplies with another gain which I have mentioned as 2 pi. So this 2 pi will multiply with fc, so this will become omega c, and similarly kf by 2 pi, there's a 2 division by 2 pi over here, so this would multiply with this 2 pi, and eventually you will get kf, and then the message signal would be just simply represented over here, right? Now this block would be then passed through an integrator. So if it passes through an integrator, the fc into 2 pi, that is omega c, would be converted to omega ct, while for the rest you would have kf and the integration block, because the message is dependent on time. This was constant, this was independent of time, but the message signal is dependent on time, so we have an integration appearing over here. All of this is basically fed into a cos function which I have expressed over here. Also note that I have used a discrete time integrator, but you can also use, preferably that you use a continuous time integrator. For a later work, I have considered just discrete time integrator in this simulation, and eventually then we would pass it through a gain which is just unity, so it will not play any role over here, and the output of this is fed to a scope,
At the same time, message signal is also fed to a scope. Also, the message signal is fed to spectrum analyzer, and the frequency modulated signal, this is the output, is the frequency modulated signal, so this is also fed to the scope. So if we simulate it, right, so we have a time domain signal over here, and this is our message signal, the upper plot in time domain, and this is frequency modulated signal. So let us zoom on the x-axis, say until here. So whenever the amplitude is high, the instantaneous frequency will be higher. When it is low, it would be lower. So this is reminiscent of a frequency modulated signal. Now in terms of spectrum, we have, let me again zoom this one. So let's take it until minus 50 dBm. Remember, dBm is simply 30 plus log 10 of W. W is just watts. So we have two curves over here. The first one is this golden curve. So this golden curve is appearing from our message signal, which is a baseband signal. So it's called baseband because it is centered at zero frequency. This is a low frequency signal. And then we have an output of a frequency modulator, which is appearing over here in this blue line. Note that the blue line is roughly centered around 20. So this is the carrier frequency that we set, right? Now consider the bandwidth of this one, the bandwidth of the passband signal, the blue one. So the bandwidth of the passband signal is roughly it is actually by definition the maximum frequency minus the minimum frequency. So over here we have roughly around maybe 28 hertz. See, you can remove this section and you can remove this section, so roughly around 28 hertz. And the bandwidth of the baseband signal is generally this bandwidth divided by 2. So if you divide this by 2, so you would have around 14 hertz, which is over here. So 14 hertz means it is going to start at 0. Bandwidth is just for the positive frequencies, so it is going to start at 0 and it would terminate at, right.
Some solved examples of FM and PM are given in this video.